we are going to start today's session now. I welcome Nivedita ma'am once again. Ma'am, you can start the session. Nivedita ma'am, I hope I am audible. Yes, ma'am. Your
Yes.
mic is on now. Yes. Ma'am.
Okay.
Okay.
Sure.
Sure.
Good afternoon, everyone. So today we will, today we will be starting with the second session, and let me share my screen. So yes, is the screen visible to all of you? Can you see the PPT?
Yes, it's visible.
Okay. Thank you. So today is the second lecture for the quantum computing and technologies. And so initially we will be starting with a few recap that what we have like gained knowledge about. Post that we will continue our session. So a few things that are very kind of a, there is a misconception which we tried to clear out yesterday was uh, quantum computer, it is more powerful than classical computer in terms of all tasks. But we have seen that, or we have known that right now, that it is not really suitable for all tasks. There are a certain type of task for which we might need a quantum computer. So that means there has to be a feasibility analysis and a requirement analysis before we take up any use case. This is very important. The second one is we can replace all our existing computing paradigm with quantum computers. That is, whatever we do classically right now or in nowadays, we can actually replace the whole stuff, all task, all algorithm, everything, and can completely migrate to quantum. Is it true? Again, the answer is no. So you cannot really rely on a fully quantum computer or that kind of a setup. That is not possible and not even required. So what we can opt for a real implementation or use case is to opt for a hybrid solution. But definitely there will be a particular, say, subtask or subroutine for which we might need the help of a quantum computer. But it definitely cannot replace everything that we have in classical. For example, the second statement has a very good implication for quantum machine learning, where if you see the nowadays whatever inventions or innovations are taking place around QML, you can see that maximum applications are hybrid, and only a few subroutines maybe where it is very compute intensive, we are looking for a quantum solution. Otherwise we are just keeping the classical ML solvers, optimizers, whatever we have. So for the initial or say pre-processing, post-processing, mining task, we are actually not relying on quantum. But a few tasks are there for which maybe say principal component analysis or say support vector machine, or a few tasks are there likewise for which we are relying on the quantum counterpart. Then comes the third point, that is all hard problems. We know what is a hard problem. Just remember the example of TSP, which is one of such hard problems based on the Hamiltonian cycle. So all hard problems, particularly I'm talking about NP hard problems, can be solved by quantum computers more efficiently. So is it a true or a false? The answer is we cannot comment about it, because a few hard problems are there for which quantum computers are already able to make it as a better solution. It can outperform the classical counterpart, but it is not really proven yet. So you cannot really perfectly map between a classical and a quantum in terms of the efficiency. We have to check it out, right? And also, the catch here is, if it is a hard problem, then it is better to try out using a quantum computer. Some sort of advantage or supremacy we might actually prefer. Otherwise, there is no meaning to uh, without any reason to opt for a quantum version, because it is very very costly. Until now, it is there is no very cost effective or lesser cost type solution or a computer that is available. Even buying a full-fledged quantum computer also is very costly. So what IBM also provides is a part-time solution kind of thing. So you have to actually buy for just to use a fraction of their machine for a particular time instance, and accordingly you have to pay. Okay, so that is why we have to be very choosy, and we have to be very particular, and have to do our initial like mapping the problem statement with the real implementation, whether it is really suitable or not. We really have to map it. If it is a sorting problem, we do not actually need a quantum computer, maybe. If it is a structured data set or sorted data set, we actually do not need a quantum computer. Why? Because binary search can already solve it in a very easy time, in a logarithmic time. So we don't need a quantum computer. So where do we need it? We need it for an unstructured data set, where without use of some auxiliary memory, it takes order of n amount of time, whereas on the contrary, quantum takes order of root over of n number of times, so or number of query. So that is some sort of quadratic speed up that we can get. So we have to be particular. Not all problems, we don't have to pick up any problem, and we shouldn't want to convert it or migrate it to quantum. Next one is, quantum computing always offers exponential computing advantage. No, the exponential advantage is known as supremacy, but definitely quantum does not always offer supremacy. Rather, there are a lot of such applications or real problems where you can see that classical system actually outperforms. Whenever we were doing the experiments also in PwC, you have seen a lot of such scenarios where we have seen that though we are using a quantum computer with the same capacity whatever we have for a classical and a quantum, depending on the substructure, of the problem or its specific features, we have seen that quantum is not outperforming the classical. Rather, a classical is better. So what I am trying to say is, you have to do the experiments, have to check. Only there are a few paradigms already existing. If you can map it or match it, then you can use it. Otherwise, you have to test it. Another example I want to give it to you. We also started exploring quantum natural language processing, which is very new. You know, also NLP, this technology is also not very old, and quantum NLP is very, very new. But though quantum, theoretically, we are claiming that it offers exponential advantage, but when we are doing the experiments, we have seen that it is not at par the classical ones. So what is the conclusion here? That is, it is very, very much infrastructure dependent technology right now. Platform, infrastructure, these things we have to consider every time whenever we will be opting or try to adopt a quantum counterpart. This is something we have to keep in mind, because the QNLP one, that also where for 150 sentence only we could parse through a quantum computer using the QNLP algorithms and all. Right? So my point here is just to tell you that you have to learn the technology, but you also have to be very particular about its usage. Okay. And the next one was the quantum mechanical paradigms, where we have seen the fundamental of superposition, entanglement, no cloning theorem, and also that one very basic of teleportation, as well as measurement, which I also want to talk about measurement today, maybe through some maths and all. That is our plan that we will be doing. So, but definitely we also have seen that quantum computing is one technology which is fully built up on the non-deterministic model of computation which is offered by only the quantum physics or quantum particles. And definitely it happens in quantum level, or say nano level or micro level, whatever you say, but it is not in the macro world. So whatever or the way we measure the classical physical observables around us, that is not same as that of quantum. So here all the operations, all the manipulations, everything happens quantumly. And another very important point is, which you also need to remember today, is like for today's class, is here everything is very very much time dependent. So ultimately we prepare a quantum state, and then through the evolution of time we actually see that what are the changes that is taking place with that quantum state. That is very important, right? And from the initial quantum state till the final quantum state, whatever are the changes, accordingly we actually understand the quantum understand the kind of calculation that you want to do. Okay. Okay. And next is, we have seen the quantum superposition, where these are already we have covered. So I'm just being a little fast here. I hope you can, like, these things should be okay with you. If you have any problem, you can ask. That the queries was, can system exist in multiple possibilities simultaneously? The answer is yes. And that phenomena is known as superposition, where basically I mean this. Just a minute. Yes. So this is how we represent a superposed state. Say this is a mixed state, mixed quantum state. So this is alpha, say ket0 plus beta times ket1. Okay. Where alpha and beta, they are nothing but the probabilistic amplitudes. Okay. This is not the probability, this is the probabilistic amplitudes, and we believe that alpha square plus beta square should be equals to 1. But what if it is 50-50% superposition? That is, say ket0 can occur 50% of time and ket1 can occur, say 50% of time. So in that case, it will be ket psi will be not half, rather 1 over root over of 2 ket0 plus 1 over root over of 2 times ket1. Right? Because 1 by root 2 whole square plus 1 by root 2 whole square should be equals to 1. So this is the possibility that I'm talking about. So this quantum state has a possibility to hold this state as well as this one. So this is a 1, this is 2, and it can hold both these states together. So that is something that I mean by multiple possibilities simultaneously. So the answer is yes, it can hold them. So similarly, if it is a 3-qubit system and I want to realize superposition, so it will be, say ket psi is equals to, say alpha 1 ket000 plus alpha 2 001, alpha 3 010, alpha 4 011, alpha 5 100, alpha 6 101, alpha 7 110, plus alpha 8 111. So you can see there are 1, 2, 3, 4, 5, 6, 7, and 8. So there are in total 8 pure states or basis states that can exist in superposition. So if I ask you in this particular setup, what will be the probabilistic amplitudes, like what will be the value of alpha 1, alpha 2, alpha 3, assuming they are equiprobable. That is, all of these 8 states are equally probable to occur, equiprobable to occur or exist. If I ask you that one, what it will be or how we will calculate it, just remember it is alpha 1 square. If it is like alpha 1 square, alpha 2 square something, plus alpha 8 square is equals to 1. And if all of them are equiprobable, then definitely alpha 1 equals to alpha 2. All of them will be 1 by 8, this value. So alpha 1 will be 1 by root over of 8. So this is the value. Now, whenever in Qiskit, say, we will be mapping or like checking that the superposed state in terms of box sphere, then we can see that 1 over root over of 8, whatever be the numerical value, we will see that that particular value we can see as association with respect to all these 8 steps. So this is how you are getting it, right? So what is the mathematics behind it? Now you have got it. But consider we only have talked about the equiprobable one, where the probabilities that we are assuming of different states are equal. But what if that is not equal? Say, for example, that is a pure simple mathematics, nothing else. See, if I tell you, say, K0, like the probability that K0 will occur is, say, for example, 2x than that of the probability that K1 will occur, right? So what I'm telling is, let me just write the maths here. So what I'm telling is, I'm just giving you a simple math. So the maths is K0 probability is 2x times the probability with which K1 can occur. Now, if I ask you, if psi is equals to alpha K0 plus beta K1, then find the values of alpha and beta. Can you do that? This is very easy. So this is the case for a non-equiprobable, where they are not equal. So remember the same policy for here as well, where K0 probability is 2x times K1 probability. That means, say, for example, probability means the probability of K0 is not alpha, it is alpha square. And K1 is not beta, it is rather beta square. So this has to be equals to 1. Where K0 probability is 2 times this one. So this is 2x, say, the probability itself. So 2x plus this is x. Okay, this is equals to 1. So 3x is equals to 1. So x equals to 1/3. That means beta is equals to 1/3. So, sorry, not beta, rather beta square is equals to 1/3. So beta is 1 over root over of 3. And similarly, that will be for alpha. You can do that. So likewise, it can be mapped, it can be like anything, it can be like only 2 states I have shown to you, it can be like 8 states, even more than that. Whatever it is, it will be always the same. Just remember one thing, that the like square of the probability, like summation of the squares of the probabilistic amplitudes, or in easy words, the summation of the probabilities will always be exactly equals to 1. That this is called the normalization constraint. Okay, I hope it is clear. Let me go back to this point. So next part is clear. What is the mathematics behind it? Now the next one is how real the phenomena is. Of course it is real. That is the power. And how we can realize it, I just have shown to you. Whatever be it, remember the like finger story. Like our hand is one quantum state. It has 5 fingers, which is equivalent to the 5 qubits that we have. And each finger can be either up or down, meaning either off or on. So likewise, in our hand only, in one hand, we can actually map 2 to the power 5, that is 32 encodings, using only 5 qubits or 5 fingers. So definitely it is realizable. And next is the relation between classical bits, say 5-bit register, versus classical state, say 00101, that is only one classical state. versus qubits, that is a 5 fingers, so number is 5, versus quantum state. Quantum state means the superposed one, right? That is my hand altogether, versus the quantum states, which is my each of the like 32 states. So they are also quantum, but that they are also pure. It is not mixed or it is not superposed, but they are also basis state or pure state, versus one single superposed quantum state of basis states. So this is that side that I'm talking about, which actually, if you take the count here, that count will be 32. Okay. Why this is very important for you to know is because of these are the fundamental like building blocks. So whenever you will be continuing with the other like qt next qt sessions, whatever you do like quantum algorithms, quantum ml, quantum optimization, you will be seeing exactly the same property. This is very fundamental property of quantum physics, and this is how we actually map it in quantum computing, right? That is why understanding this thing, understanding the mapping between classical bit and quantum bit, what is a classical state, what is a quantum state, how the like probabilities you can adjust, and how to do the interference that I have talked about. You remember yesterday we were talking about that. Say right now I am thinking about three different mood. I have three different moods simultaneously that I'm holding. Either I can have a chana masala, or I can take my child to doctor's room, or I can say want to watch a movie. So this is all existing together, and if I am a quantum system, then I have 33.33% probability of thinking about all the different things together. But what happens whenever you ask me, I will be giving you exactly one solution. Now, what solution I'll be giving to you? That is, if you don't do any tampering, if there is no manipulation, then it will be perfectly random. Exactly the same thing happens with quantum. So, if you want me that I answer you that I want to have a chana masala, not anything else, not like watching a movie, then you have to manipulate my mind. Similarly, here also, if you want to manipulate that what quantum computer will be giving as a result to you, you have to manipulate that quantum logic. And how you can do that? That coding is you, what you can do is through the quantum algorithm. That is the logic. But if you don't do anything, the output that it is going to produce, it will be perfectly random. And also the order will be random. So I can tell you like chana, then doctor, then movie. Next time, if you ask me, I can tell you like movie, then chana, then doctor. What I will answer in what order? 1, 2, 3, 3, 1, 2. That also is random. Okay. That is the beauty of quantum measurement. That you have to do certain sort of tampering. Otherwise, it will happen as the way nature works. Because it's very much how nature works. Nature works quantumly, and quantum works in exactly the natural way. Okay. Then we have seen that what is quantum entanglement. We have I have talked about the movie Judwa, that Salman Khan picture, that was some sort of entanglement. And we also talked about a maximally entangled pair, or the Bell state. I have written only one Bell such pair, but it can actually exist in this way. Say ket 0011 by root over of 2, then it can be ket 00 minus 11 by root over of 2, then it can be 01 plus 10 by root over of 2, and it can be 01 minus 10 by root over of 2. But how you can prepare these Bell states, that is something that we will be today discussing about. That how we can actually create or generate any quantum state. That can be either the initial state, that can be maybe the final state, or that can be any intermediate states. Intermediate means anywhere during the time evolution of the quantum states. So that can be anything. But with some basic gate manipulation and realization, we can actually create any arbitrary quantum state if it is given to you. We will look into that. Next one was again, out of all possible states, how to measure one single output state. I talked about it, right? In algorithms, we will be having a detailed understanding of this thing, how to do the quantum measurement. So what is behind quantum measurement versus the classical theory? I just have talked about in classical, there is a way to guess the output. In quantum, if you don't do anything, just prepare a quantum state and directly try to measure, you can get any output. And exactly that any output thing, that inherent randomness in measurement has a beautiful interpretation in random number generator. Now, since we are doing using quantum, we call it quantum random number generator, nothing else. Where there is basically some quantum device, okay? There is some beam splitter or anything you can imagine. There is, say, some plate, and you somehow is actually mapping that what output you are getting. Now, it can be either zero, it can be either one. Say, this is in the first hop, this is the second, third, fourth, fifth, sixth, seventh, eighth, and likewise, so on. So it can be zero, say, then one, then again zero, then one, then zero, then one, zero, nothing else. Likewise. So that means since you do not know that whether one quantum photon or quantum particle, if you measure it, whether it will be a zero or a one. Now this is a problem, right? But since it is very much absolutely, theoretically, inherently random, we are actually use this thing in order to prepare a quantum random number generator devices. So this is exactly what we do. Now you will say that, okay, is this really that easy? That means if we only plot it, say a Python function, we'll be just taking say 10,000 values of zeros and ones. So will it be perfectly random and it will be a random number generator? The answer is no. Why? Because there are certain clauses. What are the clauses? There are a lot of statistical tests like entropy, how many, say, chunks of ones are there. If it is lot more, then there is a problem. So basically, for these kind of testing, for each of those tests, you have to put 10 million number of bits. So for one shot. Similarly, in another shot, you have to put again a stream of 10 million bits in a file, zeros and ones. So after this thing, there are a lot of post processing that you have to do. Or post processing, in easy words, you can understand as a statistical, say correction, say bit correction, statistical bit correction that you have to do. But this is the starting point for that. So at least one thing should be clear to all of you, that if I have one qubit or one quantum bit, and if I measure it, I cannot guarantee that what will be the answer. But another twist is there, that assume that all our these discussions are only based on the noiseless quantum hardware. If the device itself is faulty, that means whenever I have prepared the device, maybe by default I have a bias towards zero. So maybe I can get, say, 60% of the times I'm getting a zero, or 80% of the times I'm getting a zero, and only 20% of the times I'm getting a one. So that is something that is not really very natural. That is your measurement error, or say the preparation error. That is a separate thing. But whatever we are assuming is, once we have the error corrected quantum device where there is unbiased setup of zeros and ones, it will behave in this way. That is what our assumption is. And then comes another beautiful theory, which was quantum interference, where there are two different types of interference. Let me just, I talked about it theoretically. Today I'll be talking a bit about it mathematically as well, so that you understand. So quantum interference can be, so interference, you know this word, like interference means just to somehow tamper, or trying to alter, or just trying to somehow manipulate or do something with the existing system. We call like don't interfere me. So that is basically what interference is. Now, in context of quantum, what we mean is there can be two different types of interference. And basically, also in bonds, or lake, you have seen the phenomena called interference. If you have seen it, have you seen the bubbles or that kind of waves ever? So two different kind of this thing, something like that. I hope all of you have seen that, something like that. So often these kind of some fringes are there, and often due to these crossing over, what can happen is either its strength will be increased or its strength will be decreased, meaning one small wave can be a big wave or one wave may be cancelled out. So whenever it is a bigger wave from a smaller wave, we call it a constructive interference. And otherwise, if it is cancelled out, we call it a destructive interference. Destructive interference. Now the thing is, mathematically, say I have a quantum state where I can write it. I'll be using separate PPT as well, but just because I'm explaining the slides so that you can actually recall. Whenever you will be looking into the slides, you can recall it. But it will be a bit clumsy, but I'm not using any separate slide right now. Says ket psi is equals to uh, chana. Chana example, let me take. Say, okay, say point 0.3 something or 33 actually. That is what I want to take. Say chana plus 0.33, just ignore it, will be 0.99, but I'm just assuming that it is actually 1, or it should be root over, I guess. Yep. Times, say doctor, uh, and something, say what movie. Okay, likewise. Now say I'm telling that, okay, I don't really in a mood to go for watching a movie. Consider these three possibilities I had initially. Okay, now I'm telling that I am not definitely in a mood to go for a movie. That means what I am left out with, only to have chana or to go to doctor. But the thing is that whenever it is, I'm cancelling out one of the options, which is destructive interference, what will happen? My probability of having chana and going to doctor will increase because I have to maintain that normalization constraints and all, right? So remember, in this way, the destructive interference, if one probability or one possibility gets cancelled out, it always increases the possibility or probability of the other quantum states to exist in superposition. And similarly, just on the contrary, if I add one more, say movie is there also, and then I'm telling you that, okay, I can also, maybe I can go for going up reading a book. Okay, some probability, say I'm not writing it, and ket b, this is probability of reading a book. So this is having chana, going to doctor, having some going for a movie and reading a book. Now whenever I'm adding up, that is a constructive interference. Can you notice that the possibilities of chana and all the other things, they are getting decreased? Why? Again the same thing. So right now, if I have four options, my probabilities, and if it is equiprobable, all my options, then it is 25% chana, 25% doctor, 25% movie, and 25% book. So now my probabilistic amplitudes as well as my probabilities will get diminished because I'm increasing, or I'm just actually adding more states in superposition. I hope it is crystal clear to you now. So what do I mean by constructive interference theoretically and as well as mathematically? So increasing a quantum state in superposition is a constructive interference which results in a decreased probability of each of the quantum states. Similarly, destructive interference is deleting out or cancelling out a few quantum states from superposition, resulting in a more increased or a condensed probabilities of the remaining states. I hope it is clear. Now, so right now we should be very okay with a few things. I can assume, I guess, superposition, entanglement, fundamental of teleportation and no cloning, measurement, a bit of it, measurement and interference, right? And also like decoherence, in a very nutshell we discussed. A quick recap is decoherence is an enemy of quantum system. What it does is it actually, whatever you are planning at 10 a.m., maybe you are watching the property, you are watching that, okay, it is perfect like that, quantum states are working. If you measure at 1 p.m. and don't do anything meanwhile, then you will see there is a decrease in the quantum properties of that quantum states. So it decoheres, kind of vanishes. Okay, since it is photon, so it's very fragile as well. So our target is also through some repeater, through some error correction technique, how we can prevent decoherence and bring more coherence in among the quantum bits. So algorithmically, there are a lot of techniques. Physically, also we are working on that. Error correction is technique. So there are several mitigation ways that we actually adopt in order to beat or in order to face the decoherence. One very easy thing was just to let the interacting qubits be neighbor. Say I'm interacting with flat number 235 and I'm residing at flat number 11. Rather than doing that, why can't I shift at 4 so that I be close to flat number 2, 3, and 5? Similar concept like here also we adopt. Okay, so there are several means to face decoherence. Okay, and after that we started with the quantum gates, which is fundamental for quantum circuits as well as quantum algorithms. And the reversibility logic also I discussed a bit about it. Reversibility, yes, I guess. Yeah, this is the spelling. Yeah. So for AND gate, we have talked about it. So for 0 0, it will be 0, A and B. For 0 1, it is 0. For 1 0, it is 0. For 1 1, it is 1. But if I have only 0 as output, I cannot tell that what was my input, whether it was 0 0 or 0 1 or 1 0. So output 0 cannot be mapped to which input pair it was. It cannot be possible. So that is, classical logic gates are irreversible in nature. Whereas on the contrary, the quantum gates, all the quantum gates are reversible in nature. Where only one quantum gate is there, which is also there in classical, which is reversible. What was that gate? Not gate. Okay. So this was the thing. So not gate is 0 1 and 1 0. So basically gate 0 is 1 0, the column vector 1 0. So if you put 0 1 1 0 and this one 1 0, if you just multiply it, what will it will be like 0 into 1 plus 1 into 0, that is 0, and 1 into 1 plus 0 into 0, that is 1. So that means not gate or x, say, of gate 1, gate 0 will be nothing but gate 1. So it's an exact inversion. That's why it is also called inverter gate. And these are few gates that I talked about. Z, shift, this is a phase, this is shift, this is just a like pi by 4. In terms of theta, it's pi by 4, and this was our very famous Hadamard gate. Just a minute, yeah. Okay. And Hadamard, how it works? Hadamard is, just I want to show you one example. Yes. So Hadamard is, say, 1 over root 2. Let me just multiply directly. 1 over root 2, 1 over root over of 2, and minus 1 over root over of 2. This is Hadamard, right? So if this is applied on gate 0, which is 1 0 in a column vector form, just see what we get. 1 over root 2 into 1 plus this into 0, that is 1 over root over of 2, and this one will be again 1 over root 2 into 1 minus 1 over root 2 into 0, so this is ultimately 0, so it is also 1 over root 2. So that means it is 1 by root 2 1 1. Why I have shown you, showing you this is because I just wanted to mention that what do I mean by this 1 1. Okay, the 0th index and one first index. Yesterday I guess one or two people were asking about this. They might be having some doubt. So 1 0 or ket 0, this means that this particular place is for the 0th value, and this is for the, I'm not writing first, rather I'm just writing it as 1th value. Since it is ket 0, that's why it is 1 here over here and 0 over here. Similarly, if it is ket 1, it is 0 over here and 1 over here. So here, this particular ket x or ket 0 or ket 1 actually tells us the position where there will be a high. Okay. So similarly, if this is the concept, then in case of 1 1, what actually we are getting is, it means it is 1 over root 2. Just forget about the amplitude right now. So it is 1 0 plus 0 1. Of course, we can write that, right? 1 0 plus 0 1, if you add them, it will be 1 1 in matrix. So that means it is 1 over root 2. This is your ket 0. Just let me multiply 1 over root 2 here as well. So 1 over root 2 times ket 1. So what it is a superposition with respect to a single qubit. 1 0 was there. It is right now 1 over root 2 ket 0 plus 1 over root 2 ket 1. So that is the essence of Hadamard. Okay. Now, you might be asking that what if we have more number of gates? That is the increase. This is only single qubit Hadamard. Say, how to then devise a 2 qubit Hadamard or a 3 qubit Hadamard, if you ask that. So I'm just writing a 2 qubit Hadamard. Let me write here. What I'm trying to show is how to construct the bigger size Hadamard gates or Hadamard matrix. So this will be, see, I'm copying exactly whatever you have here. So it's kind of this thing. Let me draw it, then it will be easier for you to follow. In first, second, third quadrant, it will be exactly same. And let me draw a solid line here. What I mean is, I'll be exactly copying the same thing here. 1, 1, 1 minus 1. Similarly, 1, 1, 1 minus 1. And here 1, 1, 1 minus 1. And here minus 1, minus 1, minus 1 and 1. So that is a 4 cross 4 Hadamard matrix. If it is 8 cross 8, exactly same thing. Just divide it in terms of a 4 cross 4 submatrix. Then again in first, second, third quadrant, it will be exactly same. In fourth quadrant, wherever you have 1, just it will be minus 1 and vice versa. Minus 1 will be 1. Right? And another one thing that I want to mention is, if this is your ket 0, then, and yes, I just there's this 1 over root 2, that also will be adjusted accordingly. If it is like 1 over root 2 for a single qubit, then for 2 qubit it will be 1 over root 2 into 1 over root 2, that is 1 over root 4, which is half. If it is 3, like a 8 cross 8 matrix, then it will be 1 over root over of 8. If it is a 4 qubit, then it will be 1 over root over of 16 or 1 by 4. Of course, that will be adjusted. Just you keep on multiplying it with 1 over root 2 if you just increase the Hadamard size in power of 2. Okay. And if this is your ket 0, just one thing, what will be your ket 0 0? That is a 2 qubit one. It will be 1 0 0 0. Just understand indexing. This means this is your 0 0th or 0th. and that is high. That is why it is QT-00 and representation of QT-00. This will be high when it is 0, 1 or 1. This will be high when it is 1, 0 or 2. And this position will be high when it is 1, 1 or 3. Okay. Okay. And these are just a few gate equivalences. One thing I want to just mention, there might be a few slides that are common, because yesterday I have not deleted any further slides which we couldn't cover yesterday. So, but today's class we actually have added those slides because I'll be discussing about it. So there might be a few slides common. Don't get confused. Like, you just have to understand the concept. So these are about the gate equivalences that I was talking about. You know Hadamard, you know Z, you know H. Just keep on multiplying it. We'll be getting this not gate, right? So you can practice, you can create any kind of such things and check whether it is gate equivalence or not. What you need to do for this, like whatever you already have learned in QT-00 initial days, or you already know, that is the basics of fundamentals of linear algebra. Just the matrix multiplications, nothing else. And of course, you know, like there are compatibility issues and all those stuffs. You cannot multiply if it is a mm, like that m into n thing. If it is m cross n and p cross say m, you cannot multiply it. So at least this column and this row has to be equal. Just after that, it is a basic multiplication. Another gate we talked about, this was a C0 gate. I already discussed about it. So just the truth table I want to draw. If this is control, this is target, and this is your input, because C0 is a two input quantum gate and very useful for a lot of algorithms, primarily for entanglement. Okay, because Hadamard and C0, this pair together, this pair together, these two gates applied subsequently actually brings the entanglement or the Bell state. We will look into that. Okay, so control and target as input and control target as output. Two input and two output gate. Now, if it is 0, 0, it will be nothing. If it is 0, 1, it will again be nothing. Why? Because my control is 0. Need not to do anything. But if my control is 1 and target is 0, then control will remain 1, but target will be flipped to 1. Similarly, if my control is 1 and my target is 1 or was 1, then control will remain 1, but this target will be flipped to 0. This is a CNOT gate. And in a quantum circuit, this is how it looks. So this represents the control and this represents the target. Okay. So this particular, if you just give some annotations or something, it will actually, it can also look like that. But I have told you, like you can check, I don't know if you have checked or not, that just pick up any random quantum circuit, you will see these gates and these CNOT gates, how like frequently they are used. You have to, if you have to understand any quantum algorithm, you have to understand that how these fundamental quantum gates work. Okay. Okay. C phase gate is exactly same, just the case is here it is a -1, so it is exactly same. Only the difference is that if your control and target, it is also a two input gate, so C and T. So if it is 0, 0, nothing, 0, 1, nothing, no change. If it is control is 1 and target is 0, then also it does nothing, because it is just to change the phase. So 0 plus 0 and -0, that is irrelevant, so it will just keep it as 0, no change. But if it is control 1 and target 1, then control will remain as 1, but because of the control as 1, your target will now become -1. That is, this is the phase shift. By what angle? By an angle of 180 degree. That is the -1. Because e to the power I pi is basically cos pi. of that XOR sign, it is this one. Okay, so that is the C phase gate. Now let me just, before I enter into Toffoli, let me just once go back. Just short quantum circuit realization I want to show it to you. Say the Bell state one I was talking about, right? So what was the Bell state? It was 1 by root 2 800. Let us pick up this one, the very easy one. This is the very basic entangled pair or the maximally entangled Bell state. Okay, so how we can realize that? And this is entanglement. So I've told you, for entanglement what you need, you definitely need what? Two quantum gates at least for the basic entangled state, that is an Hadamard as well as a CNOT. So how you can do that is, so definitely there will be a two qubit. You can see that qubit number 1, qubit number 2, and this is also qubit 1, this is qubit 2. So let me write, this is qubit 1, this is qubit 2, this is the same qubit 1 in a different state, and this is qubit 2. So let me just draw, this is a qubit 1, q1, and this is q2. So initially this is the first qubit, this is the second qubit. So on the first qubit, let me apply one Hadamard gate. Okay, and then whatever was the output of the first qubit, just put a CNOT gate here, where this first qubit will be my control. This is a CNOT gate, right? Now let us see what happens.
Madam, your presentation is not visible.
Okay, so from like for how many minutes?
Just now, 5 minutes.
Okay, I don't know why. Let me again share it. Just a minute.
You can share.
Yes.
Yes, madam. Now it is visible.
Great. Okay. So initially this was your ket 0, and this one also was ket 0. And on first qubit you have applied your Hadamard. Just check what was the output of Hadamard. The Hadamard output was this one, right? 1 over root 2 ket 0 plus ket 1. That was the application of Hadamard on ket 0. This is your ket 0, 1 0. This one. So just for the sake of simplicity, I'm just not writing the 1 by root 2 part. So it will be, after this thing, it will be ket 0 plus ket 1, right? And this qubit will be 0. I have not done anything on this. So this is nothing I've done on that. So that means my first qubit will be, after Hadamard, ket 0 plus ket 1. And my second qubit will be tensor product ket 0. Right? So if I just like write in a better way, then it is 0 0, this 0 and this 0 plus 1 0 after Hadamard on 2 qubit system. Now if I apply the control like CNOT gate, where this one is my control, I'm not writing the target other of, because of course the second qubit is target. So for 0 nothing will happen. But if my control is 1, then target will be 1. So we got our Bell state. 1 over root 2 I just have not written here. It will always be there. I'm just not, like, for sake of simplicity, I'm not writing it. Okay. Now similarly, if it is say ket 00 minus ket 11, then after this you can plan for using some C phase gate, because you now know that C phase gate actually changes the phase. If it is 1, then it will make it minus 1. So for flipping you need C naught. For basic flipping you need not inversion. For controlled flipping you need C naught. For controlled phase shift you need C phase. For simple phase, only applying a phase, you need just the Z gate, right? And if it is controlled rotation but not 180-degree, then what you need? You need a very generic rotation gates where you have to precisely tell that what will be the theta. So that is how there is concept of universal gates, where only by changing the parameters of say theta, you can actually realize any of the primitive gates. But definitely a few gates that you cannot like forget, that is the C naught gate and all. So C naught is one operation that is not possible, uh, like, or cannot be created by using any universal gate likewise. Okay, because flipping is a very unique operation that you can get through this, the control flipping primarily. So this is the basic of this one, like gates. And I hope that now you are realizing also, I will be talking about it more, that how you can interpret a quantum circuit, right? So generally a quantum circuit can look like anything. So this can be say 1 2 3, say likewise, mm, likewise say this thing, similarly say this is your control and that's this one is target. Just remember the field circle is control. So from only from these pictures here, what you can interpret? First interpretation, there are 3 qubits. Why? Because there are 3 lines. Definitely 3 qubits has to be there. Second interpretation, there are a few basic gates. What are they? Like two Hadamard gates and one Pauli X or Sigma X gate. We also call Sigma X gate. Third interpretation is there is two C naught gates. Next one is, if I just have to write it, let me just name it like Q1, Q2, Q3. And if I have to write it, okay, in terms of a like programming language, in a very simple language, say QCL was there, or say the very basic quantum assembly version, it will be, that is not the Python very unstructured one, but you can map it. And also don't worry about learning the Python version of all these circuits and all, because in IBM platform it will be automatically generated. So you just drag and draw a few quantum gates in your circuit, but you have to of course know the logic and know that which quantum gates in what order, or how to measure, how to manipulate the gates, that you have to know. But once you know that, you really need not to bother about writing the code by yourself. IBM has that inbuilt feature. If you just draw the quantum circuits, that also is very easy. You can just drag and drop the quantum gates and increase the number of qubits just by clicking a plus button. You can actually increase or decrease the quantum bits. And dynamically, your code, the Python version as well as the QCL version, that will automatically be written for you. So you don't need to bother about writing the code or learning how to write the code. That is automatically done. Okay. But just so that you understand that how to interpret the quantum code, it is something like, say the first one is what we are doing. Just take it over here. So can you what do you think, that what is the order of these 3 gates? Is there any dependency? No. Why? Because all of them are independent. There is no dependency. But definitely this C naught is dependent on this one, and this C naught is also dependent on all of these gates as well as this particular earlier C naught gate. So the operations are, say one is you are applying Hadamard on Q1. Second is you are applying another Hadamard on Q2. Third is you are applying NOT gate on Q3. Fourth is you are applying a C naught where Q1 is the control and Q3 is the target. So the gate or the operator name is C naught. The first operand here is Q1 because it is the control. So, and also remember, C naught Q1 Q3 is not equivalent to C naught Q3 Q1. Why? For obvious reasons, because control is the one that has to be like positioned or has to be written in the or as the first argument. So it is q1 then followed by q3, and fifth one is, and this is not equivalent to q3 q1, and the fifth one is c naught. Then what is your control? q2 is your control, so it's q2 q1, right? So this is how it works. Now if I tell you that, can you tell me that, okay, where is it? Can you tell me that this is a random quantum circuit that I have drawn on top? These are all the like specifications. This is the code. Everything we already have seen. But can you tell me that how or what is the resultant state of these particular quantum circuit? If I ask you that one, can we know that? That is also possible. Just a minute. That is also possible. So let me, where is it? Okay, let me do one thing. Just pardon me. Let me add one slide and show it to you. It made a blank slide. Wait. Yes. Okay, so it was HHX and this one. Okay, that means, okay, so this one H, H, X, then this was this thing and this one, right? Let us start. So initially Q1, Q2, Q3 all were 0. So that means initially we have started with, say, initial quantum state. That will be 0, tensor product 0. I'm not explaining what it is. I hope you already know that one. 0. Now what you have done is you have applied Hadamard on the first qubit as well as the second qubit. This is the first qubit, this is the second qubit. Let me apply Hadamard. So on this one and on this one. So this will make it ket0 plus ket1 by root 2. This will be ket0 plus ket1 by root 2. And this will be what? The x. So x will make it 1. That is the operation, that is the purpose of flipping, right? So 0 will be now 1. And these are Hadamard. After this, what we are doing, let me just write it a little like in a very structured form. So 1 by root 2, 1 by root 2 will be multiplied and it will be half. And this one will be 0, 0 plus basically 0, 1 plus 1, 0 plus 1, 1. And this one will be ket1. Now let me just actually take all of them together. So it will be 0, 0, this one 1 plus 0, 1, 1 plus 1, 0, 1 plus 1, 1, 1. So this is my output after the time interval, say t1. Okay, so this is after t1. Let me write. And this is the t1 time. Now say I have two further steps. This is after t2 and this one is after t3. Now what will happen after t2 is, see what we have done. We have done q1 as control and q3 as target. So therefore, after time t2, what will happen? This is your control, this is your target. This is control, this is target. This is control, this is target, this is control, and this one is target. So that means it will be, half will be as it is. So control 0, no operation. But here control is 1. So it will be 1, 0, 0. target will only be flipped, so it will be 100, and this will be 110. And after time, say t3, where second one is the control, so this is control, and first one is the target, right? So this is target, control, target, control, target. So it will be half 001 plus this one will be 111 plus this will be same, no change, 100 plus this one will be what, 010. Control will be 1, only target will be flipped. So this is the thing. Now what do I mean by this? These are all the mathematics, but in actual, what you can see, since there are initially all the 3 qubits, so if you don't do anything and just apply Hadamard, so you will see 000, 010, sorry, 001. Likewise, I'm just writing, say, 2, 3, 4, 5, 6, 7, 8. All are equiprobable. All have certain, like this kind of probability graph you will be seeing, or probability distribution function. PDF will be seeing that. This is if it is uniformly superposed. But after this, what you are seeing is basically only 001, only 001 will be there. So it will be, that means 001 will be increased a bit, little more, like 1, 0 will be then not there, not be. Okay. So 1 will be there, 7 will be there, 4 will be there, and 2 will be there. So only for these values, it is written like this. If you have seen it, like 111, and this is like 100. There, please check the LSB and MSB. Okay, because often it is like for a few, just a minute, for a few specifications. What has happened here? What is it? Oh, just a minute. Yes, I don't know what the printer is doing with me. Some kind of fun. Okay, anyway, so whatever it is, so for these values only we'll be watching the value. And what I tried to say is just check with the LSB and MSB. Okay, because it can be either 001. I guess there is a change, so don't get confused that whether it is like 4 or 1. Okay, just check that what order they are maintaining. In Qiskit there is a kind of, that was confusion when I was doing it. I got confused initially, so that's why I'm telling. So basically this is nothing but, also if you see, this is actually summation of some mean term, right? What are the values? Like 1, 2, 4, 7. Okay, so this is how you can actually realize any quantum circuit. Okay, let's just do a little thing. Yeah. Okay. Now it is the Toffoli gate. Okay, just a minute. I want to pause a little bit here and let me take a feedback whether all of you are understanding it or not. Is it okay? Are you all getting it? Okay. Yes. So I'm just pausing for 1 minute. If anyone has any question, you can ask. Last 5 minutes, I will try. Okay. Can you please mention that who are asking it? Dr. M. Padmavati, I guess. Yes. So, if you can just specify that, what kind of doubt? Are you asking the quantum circuit or how the measurement works? We are output of the circuit. Okay, I'm just doing it. Okay. Any other question? We actually are not putting. So whenever for measurement, you actually have to put the measurement gates for with respect to all the qubits. Then we'll be actually watching the result that 1247. No, sir. No, sir. There is no direct form for writing the coherence and decoherence. It is a factor. It's kind of a phenomena. It dependent on a lot of factors. Has two things, 0 and 1 state. Now qubit can be either 0 or 1, but initially it was a pure state. So what we have done is we have initialized it, or if nothing is there, we assume that we initialize it with a gate 0. That is the thing. Yes, ma'am. Yes, ma'am. It is 1, 4, 5, and 7. Just the decimal equivalent of whatever states you are getting. And okay, anything else? Otherwise, I can discuss about. Okay, I can discuss about another quantum circuit, target and control. Okay, that's C not one. Okay, okay, I will discuss that. Which in a 00, which 0 is the first 0 near to this symbol? Okay, okay, okay. So, do you want me to take up a few more quantum circuits and just explain that, like entire evolution of the quantum states and how output are? Okay, okay, sure, sure. Thank you for the feedback. Reading material. Okay, refer Qiskit. Otherwise, after like end of my session, apart from this PPT, I will be sharing a few links. Qiskit is for practical ones, but you can at least start with Qiskit. It will be more easier for you, all of you, from the documentation if you try to start. If we measure 001, then what happens? Now you will be getting 001. That's it. If you just measure that particular, okay, let me, okay, I got it. There are a few questions. Okay, it's still visible, right? Because it's still showing sharing. So let me just add a few more slide and show it to you. Just a minute. Let me take a few blank slides. Yep. So, sorry. Yes. So for measurement, let me start with that measurement thing. So for measurement, if you want to say measure Q1, Q2, and Q3. Okay. I got your question. Okay, I got the last one. Okay, let me one by one I will answer. First, let me like disprove that idea that okay, if you tell me that I just want to measure the state 001, what is the way to do that? No, sir. You have to like manipulate your algorithm or further logic, further gate you have to introduce. You have to null the other things out. Accordingly, you have to cancel out. Otherwise, you have to say for example it is something like that we just want to take what was my value, say 1 2 1 2 4 and 7, it was right, 1 2 4 and 7. Say I just assume it is 1248 and I just want to pick up those quantum states which are prime. So neither 2 is prime, nor 4 is prime, nor 8 is prime. And this is exactly where you have like ended. Then what you can do is you can actually feed whatever output you got. You can apply one classical subroutine after this, after the quantum operation, and just check just write a basic like prime, whether it's a prime or not. That kind of checking you can do. just to check that which of the observed outputs are prime. But in without anything, you cannot actually cancel out or do any destructive interference on 111 100 0 That is not possible. But if you ask me that how we can measure the qubits, because this is the entire state, so till now it is in superposition, you cannot precisely pick up one state. Now if your question is how we can do that, that is very very much related to a concept called amplitude amplification. You have to do that. Amplitude means a probabilistic amplitude amplification, or say probability amplification, that you have to do. And there is already one algorithm for that called QAA, which I am definitely sure that you will be learning. And this is the very essence of Grover's algorithm, quantum amplitude amplification, that you have to do. You have to selectively amplify the probabilities of a few selected states, and rest of them accordingly you have to adjust. Otherwise, the normalization constraint that will not hold. So that kind of manipulation you have to do. And also, but if you have to measure individually these particular qubits, what you can do is you can directly apply the measure gates. These are measurement gates. So because I have 3 qubits, so I have applied 3 measure gates. If I have 3 qubits and I have applied, just like for individual qubits I've applied Hadamard, similarly you have to apply the measure gates. But always remember one thing, after your measurement, all the quantum properties will be lost. Post that, you cannot directly do that kind of a superposition, or cannot assume that all of them are in superposition. So the answer of your question, which was very good question, thank you for asking that, is it possible to exactly get say 100 or 001? No, directly you cannot do that. By measuring no qubit, you will be exactly getting the value 001. For that you have to apply a technique, just like greedy is one of the technique in computer science, say dynamic programming is one technique. Similarly, there are techniques called quantum amplitude amplification which we use. Okay. Another example. Just before that example, let me just give me 1 minute of time. Let me just explain it, then I will add this one as well in the example. So Toffoli gate is one very important gate. So this is kind of an extension of C naught. So this is very easy, not that difficult. So this is controlled control NOT gate. Okay, let me write, it is controlled control NOT. So by the term you can understand that there has to be multiple control. Exactly the same thing. It is a 3 input gate. It has 3 output, and definitely the first 2 are the control, or 2 control is there and 1 target is there. So here, until and unless all my controls are 1, I will not be doing anything. But whenever my true control like AB both are 1, if that is the case, then what we will do, we will simply flip the target, and if it is 0 we will make it 1, if it is 1 it will make it 0. That is it. Rest of it is exactly the same. So since here also we have 1 2 3 4 till 8, so 7 and 8, only these 2 positions will be affected. That's why you can see the effect of a NOT gate here, 0 1 1 0. And otherwise till this part, let me just divide the matrix in 2 parts. So in the upper part you can see it's just an identity matrix, no change. Just the lower bottom half, it will be 0 1 1 0, which is that kind of a NOT gate. That is a control NOT. And how does it look like? It look like this. So in C naught there is 1 control and 1 target, but in CC naught or Toffoli you have 2 control. So this is your CC naught gate. Now you can ask me one question, that is, So why do we need to do this C naught? CC naught. C naught is already there. It is just a basic simple extension. So this might sound stupid to you. And there is another similar kind of, just like the phase one, there is a fret key gate, or for the control swap gate. So two level we have actually tried of extending. But your question should be why? The answer is there is no such rocket science behind that. These are the few gates. Controlled logic is very much in use. So that is why actually we study it separately, so that every time we don't have to go for the decomposition, because anyway every time it's a very decomposition. But high level, whenever you are designing an algorithm in a high level, so if you have to write that code in that much granular level, it will badly increase your size of code, or increase the complexity of the circuit. But in physical level, they are always decomposed. But definitely applying the same logic, you can have, think of an expansion of like c to the power 4 not gate. Okay, you can think it of c to the power 4 not gate. A quick note: if cc not gate, how many inputs you have total? 3. So c square not has 3 qubits. It's a 3 qubit gate. So if that is the case, then c to the power 4 not gate is how many qubit gate? It's a 5 qubit gate. Because c to the power 1 not gate is a 2 qubit gate. So similarly, if I ask you that if you have only n qubits, total n number of qubits you have, then maximum how many, what can be your this control not gate size? It will be c to the power, where is it? Every time I'm just, yeah. So it will be c to the power n minus 1 not gate. Because c to the power n minus 1 not has actually n number of inputs. And in order to feed n inputs, you need n qubits. Okay, let me now take one example where I will try to incorporate all these quantum gates. Okay. Say this is Hadamard. Now this is say X. Let me randomly write it. Say this is Hadamard. And then say this is basically C naught, followed by this thing. Say after that, here you have applied a Z gate, and say now after that you have applied another X gate, and here after that, okay, let me also write a few gates here. So now here also you have applied a X gate, and here you have not done anything. And from this, there is a C naught gate. Why I'm choosing only X and Y, Z, why not Y? Because Y gate is basically something in the imaginary plane, so there will be unnecessarily that IY kind of those things. Definitely for like calculation, we cannot visualize it, because whatever we can visualize are mostly on the Z axis of the block sphere. What I mean is, if you remember the block sphere, so only in terms of the 0 1 axis, I'm just drawing it in 2 dimension. So only in this level we can do the measurement. So, and this is the Z axis, and this is the XY plane. So Y gate is something on this. So we cannot really understand the effect of applying the Y gate, okay, or visualize it. That is why I'm just picking these precise gates. Okay. So let us assume that this is my circuit. Nothing is there. So let me start with say 0. I'll be little fast. After that, I will be going back to chat, and if you are having any question, I will be. But if you want, you can also like write it down in your copy as well with me. So ket 0 here, it will be ket 1, and okay, till this point let me start. So this is a T1. Let me just draw this. T2, T3, T4, This is T5 and this is T6, and T6 is that level where we are also doing the measure gate. This is my measure gate. I'm just broadly drawing it. Instead of writing 3 measurement gates, I'm just drawing it in this way. So 0, 0, 0, let us start. So it is 0, 0 and 0. Then it has become 1. The middle one has become 1. So it is 0 plus 1 by root 2. This is 1 and this one is 0 plus 1 by root over of 2. Then after T1, okay, this is after T1. Then 2 to 1. Okay, so 3. Okay, we have to merge it now. Say half. So it will be 0, 1. Okay, let me just 0, 1, 1, 1. And this one will be 0 plus 1. Okay, so this is half. This is 0, 1, 0. This is 0, 1, 1. This is 1, 1, 0. Don't change the order. Please be precise with that. If you change it, it will be a C naught, C square naught. So everything will be messed up. Okay. So 0, 1, 0. Just put that order. Then 0, 1, 1, 1, 1, 0, and 1, 1, 1. Now you check. Why I'm doing this? Why I'm not kept it in this way? So that I can do the calculations easily. Okay. Because and then the control target we will be understanding in a better way. Now, which one is the control? Who is my control? Q2 is my control and Q1 is my target. So Q2 control, Q1 target. Where? Yes. So Q2 control, Q1 target. So it will be 1 then. Q2 control, Q1 target. Q2 control, Q1 target. Q2 control, Q1 target. This is after your like T2. This is after T1. Now another one where Q2 and 3 both are control, Q1 target. So 2 or 3 both are control. Okay. So it will be half. Then here nothing will happen because 1 and 0 both are not 1. So we will not be doing anything. So it's 1, 1, 0 only. Plus, of course, there will be a change. Q1 is the target, right? So we have to flip this part. So it will be 0, 1, 1. Plus it is nothing. Plus this one will be 1, 1, 1. So this is after T3. Then I have applied a Z gate. A very simple Z, no control Z. If control would be there, then it will be like this. Okay, because but it is a simple Z phase gate on kit on Q0, that is Q1. So if it is 1, then it will be -1, and if it is 0, it will be nothing, right? So it will be then -110, which represent the phase. But remember, this minus you cannot see in the amplitude. If you just measure it in the z-axis, you will not feel it, this negative one, in terms of the probability distribution. Okay, but definitely this will happen. There will be a phase shift. So it is 1 and then this one is 0, so no change. This one again 0, no change. This one 1, so again change, -1, 1, 1. So this is after your T4, right? Now what I'm doing, I'm applying Q1 and Q2, Q1 and Q3, both of them. I'm just flipping them, right? And not control flipping, normal X. So flip it. 0, 1, 0. Oh, sorry. 0, 1, 1 plus 1, 1, 0 plus 1, 1, 1 minus 0, 1, 0. And guess I'm correct. So this is after T5. Now what is the last step? Q1 is now control and Q2 is target. So Q1 control, no change. Q1 control, yes. Q2 is target. Q1 control, Q2 is target. Q1 control, therefore no change. And if you measure it, it will be just getting the values 0, 1, 1, 1, 0, 0, 1, 0, 1, and 0, 1, 0. But what will be the reflection for the minus? It will just be inverted, phase shifted. But the probability distribution of all of them will be same. That is what I'm talking. Changing the phase will not really imply or affect the probability associated. In easy words, all of them are equiprobable, all the four states, but they will be phase shifted. Like 1, that is 0, 0, 1, 1, that is 3, and 2 will be phase shifted. And 4 and 5 will be on up, like on the positive direction. So if you measure it, you will be directly getting all these steps. So it will look something like this. Something kind of say it's a 0, 1, 2, 3, 4, 5, 6, and 7. So 2 and 3 and 2, it will be like this, and 4 and 5 will be like this, something like some sort of that. This is the effect of phase. Okay. Anyone, any question if you have on this one? Let me go back. Yes, definitely. But in the same line, you cannot do that. So you have to apply that thing in that way. Of course, you can do that. ANC can be control and B can be target. Inverse amplitude means it will just be phase shifted. That quantum state, in basically it is in a 3-dimension, right? So that will be inverted. There is no change with the amplitude, just a 5 and minus 5. Say for example, both will have the same effect if we don't do anything further on that. Okay. So 0, 1 is flipping, and this my 1 minus 1 is phase shift. Okay. Is it clear, the explanation and the gates and the basics of quantum circuit? Yes, 2C's mean 2, 1. 2C means 2, 1. No. It is free. You can do that. You can definitely. And also a few quantum like computers also you can use. But they are basically for the like prototype version, definitely. But you can definitely use that. 5 qubit, 7 qubit. There are a few devices that are available for free. And of course, you can do the quantum simulator. That is also there. You can use that. I'm not showing any screen. I'm just on that chat window. Okay. Yes. How to indicate 001 in sphere? Yes. So it is basically say 01. Just you keep on dividing the say you have a pizza. This is very easy example to understand. Say we have a pizza. You can either break it into two big halves. Now if you want more, then it is say 0 and 1. If you want 0, 0, 0, 1, 1, 0, 1, 1, then again you can divide the pizza in like 4 quadrants or 4 halves, 4 quads. If you want further, you have to further divide it. So you keep on divide the like block sphere is a very kind of a pictorial representation. It's not really there does not exist anything in physical existence of block sphere kind of thing. But this is how we can interpret that how that quantum space or those kind of things work. Okay. How you can get more examples? You can directly refer anywhere, like just like I have done. So once you have a good understanding of the quantum gates, you practice it, then you can create your quantum circuits. And also very good thing will be, can randomly go to Qiskit, randomly step measure, last step measurement. Okay, I will do that. So, but for getting more examples, you just can go to Qiskit and drag and drop any of the gates. Then you do your calculation by your hand for your understanding. Then you check that whether it is the same thing that is being reflected in the actual Qiskit or not. That kind of simulation you can check. Or what happens if we just flip one thing? So what, how it will be, like in a block sphere, how it will work, or how you can depict the change. And if you change the phase, then how you can depict that phase. All these kind of things. Okay. Okay, I'll be explaining a bit on the 001 question. So except that, is there any other question? And the last step, yes. Yes, Dr. Padma, the last step I will be explaining. How will represent in terms of amplitude? Represent as in you have a certain value associated with that amplitude. No? That is how you will be doing it. So that will automatically be adjusted accordingly. That plus minus whenever that will be there. So it is a probabilistic amplitude that will be adjusted. See, 000, 001, 010, these are quantum states. And the value associated with that is the amplitude. Here I am not writing it, but it will be adjusted accordingly. So basically, 1 by root over of 8 will be initially the amplitude of all the 8 quantum states. I hope it is clear. I will. Not in the middle right now. I will be. Because I have to finish a little. So any generic question from whatever I have just discussed, except the 001? Okay. I hope it is still visible. So last step. After T6 you have asked. No, after T6 we're just measuring. That is it. Oh, you want me to, I guess this one. So this one is just the, like, these are phase flipped, right? Like the phase shifted by 180 degree. That is why I just have showed to you. This is 180 degree. These are phase shifted, nothing else. By application of these gates, you can actually invert these two quantum states amplitudes. Okay. One thing I want to tell. Say initially you have nothing. That pizza. You don't have anything. So this is one qubit. One single qubit. So what it can be? It can be either 0 or 1. Because every qubit has a possibility to hold 0 or 1 or both 0 and 1. So I'm just assuming it is 0 and 1. Now say, so these are two quantum states that you can represent. With one qubit, two states. Let me write quantum. So this is a pizza. Now let me again divide it in another division, horizontal division. Then your this 0 will now become 0, of course will be there, then it will become 0 0 and 0 1. And similarly this one will become 1 0 and 1 1. So whenever you have two qubits, just assume something like that. Say they are just, say you are spinning something, spinning two balls, and it can be the red or blue, and both the balls can be either red or blue. I mean, in the best combination possible. Maximum how many different variations you can see? You can see something like this, right? So this part red, this part blue, this part blue, this part red, or something like that, like 4 different versions you can see, and 2 different colors, of course, like red and blue. Now, similarly, say if you again spin another one, this is in the physical level, and this is in the interpretation level. Say this is the first qubit, second qubit, and mathematically, what do I mean is it will be 0 and 1, and for one qubit. For another qubit, it will be another 0 and 1. So it has a possibility to hold 4, 0, 0, that is red, red, 0, 1, that is red, blue, 1, 0, blue, red, and 1, 1, that is blue, blue. This is in the mathematical form, and this is in the geometric, so interpretation form, and this is in the mathematical form or logical form. Now say just one more step I want to show. Say another one. So geometrically, or say blot sphere, how it will be? So again you have to subdivide it, right? It's like that. Say 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1. Okay. So here you need three different qubits. Three different individual qubits. Say first qubit, second qubit, and third qubit. But whenever you are taking all of them together, they will be this one. And they will be in a superposition. First, individual qubits were there. Now, whenever you are applying superposition of all of them and creating one single state, so it will be that one single state. And mathematically, it will be like same. I'm not writing it 0, 1, 0, 1, and 0, 1. So all those 8 possibilities it will create. But have you observed one thing? Does it really mean? Just a very basic question. I just want all of you to think about it. Say if I have, say, okay, say in my house, I have 2 kids. Are they manageable? Though very difficult, but yes, we can try. Say I'm increasing I'm not increasing the size of my room, not increasing any kids area, not any extra room that I'm adding, nothing. So, but I'm increasing one more kid, say for example. I have accommodated him as well in my room. So I have 3 kids now to manage. Or say not 3, basically it's either 1 kid or 2 kid or 4 kids or 8 kids or 16 kids likewise. But I'm not increasing. What very, very important here is to understand is we are not increasing the size of the room. Will it be little difficult to manage? Definitely. Why? Because there will be a lot of chaos within the room. They will be maybe quarreling, they will be fighting, they will be like if one is sad, another one will be happy or sad, vice versa. So there are a lot of such coupling defects that is possible if we increase the number of kids in a particular room. The more kids, the more will be their interaction, and the more they interact, they will loosen up their own power. So in terms of quantum state as well, exactly the same thing happens. So right now, this is where the hardware challenges we are facing with quantum. That ideally, theoretically, we can say that okay, we can actually prepare say 10 qubit quantum state. So 10 qubit quantum state means one state which accommodate or which actually can accommodate 2 to the power 10, that is 1024 such kids in that room. So definitely there will be a lot of decoherence and coupling error, and very difficult to manage physically for kids. Similarly for quantum, that this manage word is measure, because the precision you have to increase to a greater extent. It needs to be very, very fine tuned. Now quantum itself is so noisy, inherently noisy. It is so fragile. It is very powerful, but the power you have to retain, right? Till the time you complete your computation, you have to retain that power. Otherwise, a very powerful player, if he cannot play or if he gets out within 5 minutes, how can she perform or he can't perform? So same thing is there as well. So these are the hardware challenges. Temperature fluctuation can happen, pressure fluctuation can happen, a lot of say maybe vacuum interaction with the vacuum. If it is not perfectly vacuum, that can actually deteriorate the performance. If you do not apply the repeater, it will deteriorate the performance. If they are not neighbors, they will deteriorate the performance. They cannot hold that. And if you have to precisely think that I have to pick up what exactly my 987th kid right now is doing, is it very difficult to find and difficult to manipulate? Yes, of course. But if it is only 2 kids or 4 kids or a limited number of kids, which is under the threshold of the capacity that my house or my room can offer, then it will be easy to manage. Are you getting it? So this is the superposed state. This is exactly the superposed state that I'm talking about. So here it was, when it was nothing, it was 100% 0 and 100% or 100% 1. Probability full. So very easy to get, very easy to obtain, very easy to measure. Bias less, error chance less. Whenever it is 50-50%, manageable, of course manageable, but again, the strength of getting 0 or 1 will be exactly half, reduced. Logarithmically, they will be keeping on being reduced. Okay, because here the amplitude is 1 over root 2. Here it is 1. Here it is 1 over root 2. Here it is 1 over root 4. I'm not writing 1 by 2. I'm just writing 1 over root 4 in terms of number of states. But here, since I have 8 states, so each of the state will be having with a probability of 1 by 8. This is the probability. And 1 over root over of 8 as amplitude. So the more we can accommodate, the less power it will possess. I hope now it is very clear. Okay. These are a few things. And yes, talking of where you can get more example, you can just, as I was telling, that you can drag and draw from this kit. Just draw random gates and then calculate it mathematically using your copy, using your hand. Then whatever output you are getting, you can just verify with your this one, with the actual output that you can see there. Then the Hadamard transform, I already covered it. Quantum circuits, I think I covered a few of it as well. And as and when we actually proceed further for algorithms and all, definitely all of these things will be further discussed. Bell state, already I talked about it. Just check, I actually have designed this one. And I think now you can do this one as well. 0, 1, minus 1, 0. I have drawn this one. These two you can do as your homework. So if I have to draw 0, 1, minus 1, 0, can you do that? Ignoring 1 by root 2. Of course, Hadamard to basic, it have to do. Then a C naught. Say I have done till this part. So it will be 0, 0 plus 1, 1. Now say here I have applied one what? One up, one flip, right? The bit flip, not the phase flip. So it will be then 0, 1 plus second one, right? So 1, 0. Now say what, now till this part I have achieved everything, only the minus is remaining. So this is associated with the first qubit. So that means here I have to apply a Z gate. Only a Z, not a controlled one. So this small circuit is basically for this particular Bell state. Likewise, are you getting that whatever, no matter what circuit you are given or what quantum state you are given, the equivalent you can actually calculate if you have a solid understanding of the quantum gates. Okay, you can actually practice this 0, 0, minus 1, 1 as well as 0, 1 plus 1, 0. 0, 1 plus 1, 0 to already we achieved it. Likewise, 0, 0, minus 1, 1 also you can try. Okay, This is a list of quantum gates. I just have actually clubbed all of them together in one page. So Toffoli or control not. Swap is one gate. Swap is very easy. Swap is just whatever content of one qubit you have, you will be just like the swap 3 and 5, A and B, that kind of problem. So whatever is the content of that first qubit, it will be exchanged with the contents of the second qubit. So Hadamard, Pauli XYZ, phase gate, T gate, and control not, CZ, control Z, swap, and Toffoli. These are the basic gates. And what is single qubit gate? Pauli XYZ, Hadamard, and a few rotation gates are single qubit gates, where actually you have only one input. That is a single qubit gate. And where you employ at least two or more number of inputs, you call it a multi-qubit gates. Very basic fundamental multi-qubit gate is C0 or C phase or swap. Okay, so here actually this was from my earlier one sessions. I have added this one, so you can check this one. A lot of such quantum circuits I have drawn, and how through the time evolution, what are the states that are coming. So I think you can start practicing with these as well initially. So all of these things will be getting. You can see there 1 2, a lot of such, a few things like Hadamard, a lot of things I already discussed. So yes, so I got one question. One asked that what was for 00. I guess, what do I mean by 1000? I guess someone asked this question half an hour before somewhere. I just missed it, sorry. So 00 is 1000 represents that one is the index, or one is the indicator that it has to be high for 00. So similarly, if it is 01, it will be 0100. Similarly, if it is 10, it will be 10 is 2, right? So it will be 0010. For that value position, it has to be on. And for 11, it will be 0001. Okay. So you can check it. This example, this is a 4x4 Hadamard gate, and this is a 1000, that is gate 00. I have shown here the detailed mathematics, like the detailed multiplication. If you do that, you will be getting 1 by root 2, 1 by root 2, 1 by root 2, and minus and 1 by root 2. So take 1 by root 2 as common, it will be 1111, which is nothing but 1000 plus 0100 plus 0010 plus 0001. Okay, so that is the superposition of all four basis states will be getting. Okay. Similarly, another example you can see. This is the Bell state. You can check it again. Okay, and these are a few examples, a few questions also. This is an inverter gate. All. This is another one, that what happens if I apply 3 Hadamard. Okay, so I think right now you should be able, if you have understood today's class, you should be able to identify or understand all these examples in first shot. Just check it out once. Similarly, another example, why I have shown you this one seems to be easy, but why I have shown it, just to interpret one very important point here. I'm just keeping as a note here. Just remember that even if I have 3 qubits, then it does not mean always it will be 8 states. It can maximum have 8 states. So how it will be determined? It will be determined by the number of Hadamard gates or number of superposition gates that you are using. If you are not using for 1 qubit, say for this one, I have not used any Hadamard. So that means only this will yield to 2 possibility. This will be 2 possibilities, but this will not be 2. It will be 1. So number of gates number of states possible will be 2 into 2 into 1, that is 4, not 8. So 3 qubit or any n qubit. Let me write in form of n qubit. N qubit quantum states or n qubit, say, yes, quantum system can have maximum can have and maximum, focus on both these words, 2 to the power n number of states, and we generally call these number of states a capital N. So n is equals to 2 to the power n, where the small n is the number of qubits and this one is the number of states. Okay. Yes, similarly few more examples, you can go through that. Okay. Yes, so I think we can stop here. It will be a altogether new topic. So tomorrow or in the next class we will actually start with the quantum algorithm part. And all the first 32 slides I will be actually sending to all of you.
Slides yeah. Thank you so much, ma'am, for this wonderful talk today. Hope most of you are able to understand the mathematics behind the quantum. And it takes time. Please, again, don't get worried, don't get concerned that we are not able to understand, we are not able to follow. It takes time. These things will be repeated again. And in the next lectures in Foundations of Quantum, again, things will be revised. Then when you go to quantum computation, that is QT-05, again, you will go through some of these. Some of these implementation will be discussed in basic quantum programming, that is in QT-03, right? So hopefully you have listened to wonderful, especially the mathematics, and I think it is by heart for her now. So mostly she does that, and all the handwritten notes will be shared with you. So you can open the video, follow the video again, and follow the handwritten notes, make your own notes, and then you can also be a good teacher in similar lines. So hopefully uh, uh, you can look at that. Yeah. Few questions, ma'am. Totally, how many quantum gates? I think she's left, huh? Ma'am, ma'am, can you take that one question? How many quantum gates in all?
Yes, sir. So how many quantum gates? I guess I think you want to ask the quantum states, not gates. So
No,
in
no,
total,
they may be asking a different, like, what is that?
or which question you are referring? Yes, sir.
Yeah, that one, that same one that you're looking at.
Yes, but I'm not
How
getting
many?
the total. How many quantum gates for which question you are referring?
Yeah, quantum gates means like each of the gate you have described. No, totally how many gates? That's the count. Like the Toffoli gate or C0 gate, like that. Somebody has written 12
Yes,
gates.
yes. No, there are. See, that depends on the platform. Exactly, ma'am. That depends on the circuit requirement, and that depends on the platform as well. So maybe in Qiskit it is one. So there is no such fixed count that. Okay, I got your question. Like, yes, I got your question. Like, these are the basic gates. Yes, whatever in the list that I provided, these are the fundamental gates. But definitely there are a lot more derived ones as well. So depending on the requirements, they're increasing a few gates just for the easy access. Every day they are actually changing the or kind of revising it. Just as I said, that Toffoli was initially not there, they introduced it. So T and S are few gates which you can actually derive, but for the like, because their access is more, so they have separately picked up for a few angles. They separately have taken out a few ones so that you can directly do it, and you don't need to really work a lot or change the logic. Just you directly can apply those gates. That depends. There is no such specific ones, but definitely what we discussed, Hadamard C naught, C phase, controlled, that controlled logic, the swap logic, all these things are basic one. It means we are fixing the output. We are not fixing the output, but definitely what we want accordingly, we need to design the quantum circuit. That is true. It is not fixing, it is just like, yes, I told you, like nature,
Design.
quantum is natural. You have to design it. Yes, yes, absolutely. Say for example, I'm just giving an example. Say for fractional knapsack, we just want to get the maximum profit out of the knapsack. So that is why we have to fix the logic that no, if it is profit by weight, then only it will be yield the maximum result. That kind of manipulation in logic you have to do. Yes. Okay.
Can you explain how a million physical supercomputing conducting qubits
No.
translate to around
Yes.
1,000 logical qubits here?
No. Exactly what you are asking is, basically I will discuss about it tomorrow in details. There is a difference between, because of the noise and all, the logical qubit is different, the algorithmic qubit is different, and the physical qubits are different. So whatever till now we are discussing, they are based on the logical qubits. But in realization, because of the decoherence, because of the error correction, a lot of things there. So for each logical qubit has to be accompanied by or can be realized with the help of a lot many physical qubits. But the ongoing research, continuous research is going on so that we can decrease the number of physical qubits required. Otherwise, it will be very difficult for us. So whatever you are like looking around, like 64 qubits, all of them are logical qubits. And there is also one concept of algorithmic qubits, because again, depending on the algorithm or the logic, your logic, my logic can be different. So how we can measure it, how we can actually benchmark it. So there are different concepts of algorithmic qubit as well. Okay. Yes.
Yeah. So thank you
It's
so
no,
much. Yeah.
yes,
Please
yes.
go
There
ahead.
is no concept of optimum qubit. Our target is to reduce the number of qubits. Simple reason, we want to reduce cost, and it will be, that is why we are opting for reducing the number of quantum gates, approximating a few parts, and not using very like multi-qubit gates, because again it needs to be decomposed. So that is where the transpiler, the other kind of, just like in compiler also we have that optimization thing now. So here also we have that one, how we can optimize that. Say the two qubits or say two quantum gates, uh, if they are used, maybe they not actually cancel out. For example, two Hadamard, if you put, it is nothing but the same state. So all these kind of optimizations are going on right now, that how we can reduce the depth of the quantum circuit, how we can increase the flexibility, like increase the throughput, decrease the time taken, all these things, just like the optimization that is going on. Okay.
Yeah, thank you so much, ma'am, for your time. And we'll take a break here now. Tomorrow there is no class. Please note tomorrow is Sunday, so there is no class. It's a holiday. So, but the good news or for you is that the quiz is going to start now at 5:30. You can prepare and take the second quiz. For those who have not taken the first quiz, you can continue to take the first quiz also. It will be open. First time, those who are taking the first quiz, you can take it. As of now, some 530 or 540 people have taken the quiz. We are hoping that at least 750, 800 people will be there. So if there anybody who is willing to take the quiz, it is open. Please take it. And then after that, today's class is not there in the syllabus, but till yesterday, what Nivedita ma'am had taught, we have included in the quiz, and that will be there. And so you will have a third quiz next Saturday. And after that, on the last day, you will have the fourth quiz, right? So totally 4 quizzes of 20 marks each. So you have to get 80 marks. So that's what, and based on that, you will get the grades. Thank you, Nivedita ma'am. We'll continue with some doubt clearing on especially Canvas and WebEx, if there are any, and also on some people who have not joined the course as yet formally for their registration. So, ma'am, you can exit if you are having some other work. We'll continue with the participants who have doubts. Participants who have no problem with WebEx, who have no problem with Canvas, you can exit. You have got all the quizzes. Ma'am will share all the slides. Ma'am, we request you to share the slides, the handwritten slides also. Please share the slides so that
Yes.
participants will easily.